We are starting the lecture for Chapter 17, and Chapter 17 is the last of 3 chapters on equilibrium. So this one kind of like picks up some of the extra information. So we're just building on stuff that we learned in our basic equilibrium stuff, and then Chapter 16 we did a lot of acid-base stuff, and a lot of those concepts are going to continue on in this chapter. So we're just building upon old information. Okay. Let's just go up and start immediately doing some problems. So we're going to do a problem in which we're calculating the pH, but this, of course, adds a layer. So we're looking at it when we have what's called a common ion. And we'll see what this means as we're kind of going through it. So here's our problem. What is the pH of a solution by adding, I know grammatically it doesn't make a whole lot of sense, sorry, 0.30 moles of acetic acid and 0.3 moles sodium acetate to make enough water. Some doesn't sound right there, but we'll just go with it. To make, should be like with enough water, 1.0 liters. So we're adding 2 things to the mix. We have some acetic acid, some sodium acetate. It's in a liter of water. What's the pH? And there's some other background information we'd have to know here, and you're probably familiar with this from the previous chapter. All right, so just like we did in chapter 16 and 15, we're going to make a rice table. And it's acetic acid. We probably know what the formula for that is already because it's fairly common and you've seen it a lot. There it is. And what this is going to do, acetic acid, is it's going to dissociate, as all acids do. Of course, this being a weak acid, it doesn't do it very well. So we're going to write down the hydrogen that is released and the resulting base, this being acetate as a base. Now, the fact that they write this down as sodium acetate, that's very important. As you know, when sodium of anything is placed into a solution, an aqueous solution, sodium's a group 1, it immediately just takes off. It just breaks from the compound and just separates out. So you're left with just acetate, and there it is. So this is acting as a common ion. It said you had 0.3 moles of this. And now normally in the previous couple of chapters, we were always dealing with like molarities. Yeah, there might have been a time or two that we had some moles in there. So actually I am going to write the word mole just so we can see it. It's in 1 liter, so it's already in molarity. So that's fine, whatever. But that's the general idea. Okay, and then everything is going to be just as it was in the previous chapter. This is how we started, and this is going to dissociate some, and whatever dissociates off is added to the other side. And we are going to say that whatever is lost here is, yeah, it's kind of insignificant. So it's about the same. We're going to figure out how much it is, but it's about the same, pretty close. Okay, and then the final volume, as we already mentioned, is out of 1 liter, and these were moles. So these are going to become molarities. All right, now if I look in the back of the book for acetic acid, its K value is 1.8 times 10 to negative 5. And now we're just trying to solve for the X, the hydrogen, in the equation. So we can just kind of set this up and say 1.8 times 10 to the negative 5 is equal to products over reactants, x times 0.30 and that's a molarity. These are all going to be molarities, over 0.3. Looks like it, if I'm doing some quick math here, these two guys are going to cancel out. X is going to be equal to 1.8 times 10 to the negative 5. So that happens to be equal to the hydrogen ion concentration. Fantastic. It's almost like I'm done. Now the last part here is we need to figure out what the pH is. So pH, don't forget, is equal to the negative log of the hydrogen ion concentration. Well, I have the hydrogen ion concentration. I can plug that in there really quick, and pH will be equal to 4.74. Done. And that's what it is with the common ion. Now, just for fun, if we pretend this isn't here, we can do the exact same problem, except this would be x squared on top and 0.3 down here. I'm not going to ask you to go through all this math, but if we were to do that without the common ion, what do you think? Higher or lower pH? Is this value going to be lower, more acidic, or higher, more basic? Well, think about Le Chatelier's principle. By adding this to rebalance, we have to shift in that direction, right? By adding this. So that's going to prevent this from dissociating as well. It means they're going to have less of these. So without the common ion, I take this away, it's going to be able to dissociate more and producing more hydrogens. Therefore, it should have a lower pH, and it actually is. The pH without the common ion in place is 2.64. This would be a really good AP question on the exam. You sitting in a classroom and someone throwing an AP question at you saying, what is the result of adding in a common ion? Does it make it more acidic or less acidic? Good question. All right, let's do another one. Push this up here. Calculate ion concentration when common ion is added. So same deal, we're just trying it from a slightly different angle. That was the idea. So specifically, calculate the fluoride concentration and the pH when 0.2 molarity hydrofluoric and 0.1 molarity hydrochloric are mixed. So we have these two solutions and we're going to mix them together. And we're going to say they're equal parts. All right, so if we write up an equation, a Rice equation, HF, hydrofluoric, dissociating into this. So that clearly puts it in the mix. But remember that the hydrochloric is a strong acid. It completely dissociates into H plus and Cl minus. And you may remember from the previous chapter that this is the conjugate base of a strong acid, which means it really doesn't go in the other direction very well. It's not going to be picking up hydrogens, and of course it's not going to pick up fluorides. So this is a spectator, we can ignore it. So this contribution is 100% found right there. So that is its common ion. We'll go ahead and put in these values that we were given here. These again are molarities, or yeah, they're molarities. So I'm not going to bother writing in the moles and molarities. So we have these values, boom, boom. And then of course this is going to dissociate some, and it's going to be gained over here. We're going to assume it's about the same. Yeah, it's about the same. Now one thing to kind of just notice here is the hydrochloric's contribution is half the contribution of the hydrofluoric. But this is a weak acid and this is a strong acid, so they actually behave slightly differently. If we look up the Ka value for hydrofluoric, 6.8 times 10 to the negative 4. That is its given value. If we go ahead and run the equation here, 6.8 times 10 to the negative 4 is equal to x times 0.1 over 0.2, we will find that our x value is 1.4 times 10 to the negative 3, which is equal to x, which is equal to the fluoride concentration. Okay, so that is the contribution. That was one of the questions that we had. Calculate the fluoride concentration. Fantastic, got it. The other part is to calculate the pH value. Well, here's the hydrogen concentration, which really just came from here. It's the same thing. So if we go ahead and run that, the pH, I don't think I really need to get my calculator out for this. The pH is 1. Done. Now what's interesting as far as what would be the contribution from the hydrofluoric, well, it's insignificant. Clearly it's here. It's present. If I only had the hydrochloric, it would be this pH. By adding in the weak acid, it contributes almost nothing. We could go through and eliminate this and see how much would be added, and it's very, very, very small. I think I actually had that number listed here somewhere. It was like plus 1.4 times 10 to negative 3. That would be us doing this problem if this was, again, x. So this contribution, as far as this isn't really that part there, I'd be adding this into based on that. But adding this and then doing a pH, it would still be pretty much the same pH, 0.1 would be the answer. So actually, even though the concentration is twice as high, its contribution is almost insignificant. Okay, that one is done. End of lecture.